Okay, I know you're going to accuse me of always starting trouble. Yeah, well, I do, but I'm starting trouble because I see trouble. I'm not making the trouble. I am confronting that trouble. Now, I say we don't know where we are in space any longer. And you say, well, how can I say that? And I said, do you understand Fraunhofer lines? And you say, well, sure. And they are the emission and absorption frequencies, as we will see, of different molecules, and atoms and so forth. Now, what does that mean? That means that they show up in these particular specific lines. Let's take a look at some of the Fraunhofer lines. Right? Now, you see all these things? That's the spectrum. Okay. Now, when you see a line here, and a line over there, and one over here, that means it's hydrogen, let's say. And let's just take one here, for example. What do we have here? Well, this is hydrogen, magnesium, sodium, hydrogen. These are the different lines. Now, how do they know that everything is going away from us? Because they shift towards the red. So this line should be here. Well, it's going to be down here. This one's going to be over here. This one's going to be over here. And why? Because it's being pulled back to where it came from. Light can slow down. That's just nonsense to say that light can't slow down. Light will come into us at the same speed because we are pulling that light down to us at 1 electron volt per electron. All right? Millikan did the oil drop experiment on it. So light coming onto the surface of the Earth will be pulled at the same amount, yes. Light coming through space, absolutely not. So what do we see? Anywhere we look, it's slowing down. Well, obviously, because everywhere it came from, it's being attracted back to. So everywhere that it comes from slows down as it comes to us. And then we see it in that configuration. And then Einstein said, oh, no, it's going all one speed. No, it's not. It's only going one speed at the surface of the Earth because the Earth is a magnetic attractive source. It's pulling with 1 electron volt per electron. And if you have something that's huge and massive, it's going to slam onto the Earth because it's got a lot of electrons. That's gravity. It's nothing more than magnetism. And light can be sped up through a venturi and can slow down through other medium or being attracted back magnetically. You're going to say, oh, Roger, there's nothing in space to slow it down like in a soup or in a water or something like that. Obviously, there's some stuff in space. The stuff is particles emitted from the sun, and all kinds of different bodies emit particles into space. We scrub against them with the magnetic stripes that are in the Earth's ocean, and because that stripes spin through these magnetic particles, as we spin through them, it creates a magnetic field around us. That's what the magnetic field is. And that creates the attraction of those particles to the Earth, sucked into the Earth, up through the poles and out. Back around and back in. Back in. Some get flown away. Yes, I agree. Most of them come back around in. So what does that tell you? There's going to be warm spots. It's going to be warm spots, and I believe there might be a very warm spot in the center of the Earth. I'm not sure. I can't fully understand if this would create an inductive area, which, as it passed the pole, the center point between the poles, would there be an interaction? I don't know. But I can tell you one thing. We are a generator. We spin freely, like somebody was cranking us, through a magnetic soup of electronic particles. Nothing, and there's magnetic lines, and I'll show you those in a second. As we spin, that is a generator. Now, and that creates a field, and it creates electricity. What does the electricity do? It starts flowing around and creating these currents around the Earth that protects us. Now, they are talking about the magnetic field going away. It's not going to go away as long as we keep spinning, because there's always going to be these particles in space. We're going to spin. Now, it might get worse. It might get, because this is nothing more than a generator, and as we spin through these particles, the denser these particles are, and this stays the same, this will drag. and that creates heat. That creates magnetic fields. It creates heavy thunderstorms. It creates rain and hail and lightning and all of the effects that we are seeing. It creates global warming. All right, so let's take the mind a little bit off of this carbon dioxide nonsense. The carbon dioxide's there, but I'm going to tell you what, my friends, right out there it's 56,000 degrees. You think that doesn't come down there? We got 80 degrees down there and we're worried about the carbon dioxide? We got a lot more to worry about than carbon dioxide, because I think we're coming into dense space. And if this is dense and we're starting to rip ourselves through there in dense space, I don't see what we can do about it. So anyway, I'm a realist. I'm not going to paint anything with a flashy, shiny brush. What it is, and I see it looks like that's what they should be looking at. Is this temperature increasing in the magnetosphere? Are we having more magnetic anomalies, which we are? They say the magnetic pole is being pushed, and that's very highly possible. If we're coming into dense electronic interaction, it could very well push it. These are the kind of things they have to take into account. They're saying there's nothing here. Oh, it's just blank, empty space, a big vacuum. Time to realize and agree. They know already. They're always talking about the interactions, but then there's nothing there. Well, obviously it's there. If it's this kind of interaction, that is the ether Plato talked about. So time to fess up and say, we made a mistake. Light can slow down. Light can speed up. We're in a soup of electrons. Our magnetic field is created by the magnetic stripes in the ocean spinning. All right, and there they are. That's the stripes that they see in the ocean. They're magnetic. They're plus and minus. And they say they come out because of, I don't know, they kind of got some, I don't even know anymore. Reverse of the poles or something. It's not. When they come out, it creates its own magnetic stripes. I'm not certain why, but this is what they have. And as this spins through the soup, it creates a magnetic field and it creates energy. And that energy creates heat. And that heat is increasing. That's my take. It's Roger once again, Mudfossil University, again with my most favoritist, bestest, funnest thing, atomic particles. Now, as we left off, the last discussion was about, I showed what they say about quarks and leptons and so forth, and the strong force and the weak force. And then I just basically went through all of our different light experiments and showed, basically what I was talking about and making my claims. Okay, now, so that was my my claims and my statements and why I stated them, and I showed what they show for research and what I show for actual experimentation. Now we're going to go to the theory. Now, this goes back a year and a half or more. Well, it's Electron Flood 1/1/2018 is when I sort of locked down this. And this may not be right because, like I say, this goes back a year and a half. So I haven't been sleeping for a year and a half. I've come up with some different ideas, perhaps. I can't really remember what I have on here, to be perfectly honest with you. Some of it's already started to boggle my mind. I had to put a question mark up here because the light, when I originally started this, I thought I found that light was particles. I could see them in the experiments. You see them in our experiments. It's not hard to see. So are they all the same size, or are they just some spin faster? Now, that's the key. So I had originally had up here this wavelength situation where the wavelength of blue light and then green light and then red light was just short, then a little longer, and then a little longer, meaning the distance, 1240 nanometers, was the wavelength of what I was considering 1 electron volt of light. which is the same thing that Millikan, I took it from Millikan probably. I can't I got to be honest with you, I just don't remember some of this stuff now. But I ended up with 1240 nanometers was the wavelength of light that was equal to 1 electron volt. And 1 electron volt over the top of the frequency was the wavelength. That's, I've got a question mark here. I have to come back and look at it. But the reason I have to go back and look at it because maybe there is bigger particles. So that would mean 1240 nanometers, the wavelength, is not really the important part. It's the size of the particle. Is this weigh like 3 ounces and that weighs 2 ounces and that weighs 1 ounce? I don't know. You know what I mean? Like obviously don't weigh an ounce. I'm just using that as an analogy. Now, so is this a bigger particle, a medium particle, a little particle? I'm starting to think that may be the case. And I originally thought there was only one particle. Now I realize everything's dipoles. Or maybe it was dipoles at this point. I can't remember now. I've got to be honest with you. Anyway. Light is free electrons. They are free. That's what I had here. Now they're photons actually, meaning that there's a back-to-back dipole. This may not even be accurate to even bother talking about this. To be perfectly honest, now I'm looking at it. Let me look a little closer. Hold on. Well, there's a lot of things that are right. I can see 1,836 particles per proton. Yes. 918 and 918 plus and minus. Back-to-back dipoles. Neutrons have an additional electron. That makes them 1837, and they weigh one additional electron above 1 atomic mass unit, which is normally considered a proton. Now, and up here I have no neutrons. Well, neutrons are really protons plus 1 electron. And half are 1836 bits make the total. Now, Crookes radiometer works because particles smash into that black surface and stick just like they're Velcro. And the weight gets heavier and heavier and pushes it. It's not bouncing off them doesn't make them go faster. Adhering to them, collecting on that, spins that around in a circle. That's how Crookes radiometer. Now they're talking about heat waves and all kinds of crazy things. It's the particles smashing into it. Red light will not make that thing move. Let's see. Black absorbs all the frequencies, therefore all mass is added, and black pushes it. Now, the blue, I got to try to remember what I did there. Now, I'm just going to go back to this, because this is from the electron flood theory demonstrated that I told you started this whole thing. Now, I'm going to show you. This is Latham's Crazy Machines. Here it goes. Latham's Crazy Machines. I've been showing this for years. This is in quantum mechanics right here. Electron flooding right here. That is your positive core, which is being forced into the center by all these negatives, forcing it in. Flooding it, creating a negative zone around here after it becomes neutral, and then an additional electron or two creates the incoming ones to be unable to get to that positive, and they'll try, as you will see. Boom. Quantum mechanics, you just saw it right there. Electron flooding, you just saw it right there. Heat, you will see in a second. As he shakes it, they will rattle. These electrons they'll be forced, other electrons, into their zones and regions. They'll bounce all around. That's heat. They're boiling. They're pushing other electrons out from where they should be. They're glowing, just like you saw in my light experiments. And then all of a sudden, they're so violently pushed away, they become light. Now, let's look at the other one. Okay, here's another one I've been showing for years. Bruspup. Amazing resonance experiment. Nikola Tesla said if you want to know everything there is to know, look into frequency and vibration, because that's all there is when you get to the bottom of it. It's frequency and vibration. And you have to get to the correct frequency of vibration to achieve stability, as you will see. Alright, so here's what's going to happen. This is a vibration plate, and that is a frequency generator, and it vibrates it at 100 shakes a second, 200, 300, 400, and they're going to show how it increases in the vibration, and then they're going to show the pattern of the salt. Now, salt is a polar molecule, and I believe it has something to do with that. I can't say that for certain, but salt is highly polar, NaCl. So let's see what happens. Okay, what they're going to be doing is shaking that plate with certain frequencies, and that is going to make the electrons in that plate vibrate up and down, literally. And salt is extremely polar, and that's why it's shaken up and down. You know, you say, oh, it's just because of the vibrations. Well, yeah, but what are vibrations? What is a vibration? Ask Nikola Tesla. All right, I'm just going to let this play. Here it goes. Well, actually, I'm going to comment on each different pattern because it's very important to understand what you're seeing. You're actually seeing, in my mind, let me just explain to you what you should see. And anybody that understands atomic orbitals understands you have a nucleus, and then there's supposed to be what they call s orbital. It can only have 2 electrons. Okay, that's all it can have in there. Then you go out past that and you go into orbitals that have 8. They have what they call a rule of 8. Now, there's not necessarily just 8 in that orbital, which there is in the first orbital past the s orbital, but beyond that they start to get pretty complex. But you still see the rule of 8, and you see them. Watch. Don't forget that when you vibrate it, you are vibrating electrons, because nothing is free of being coded from electrons. So now the electrons are starting to shake. Boom. S orbital. Alright. Rule of 8. Locks right in at 1033. Boom. Rule of 8 with the s orbital in the center. Rule of 8 coming up again, but jiggled a little bit. You can find it if you look for it. And a rule of 8 just everywhere. Rule of 8 right there in the center. And it just keeps going up and up. There's your rule of 8. If you look around, you can find it. And then at a certain point, they no longer can maintain stability. There's rule of 8's in there somehow. You dig around, you figure it out. But you see, they keep taking on these complex patterns. As a matter of fact, well, I'll let it go a little further here, but I might as well just show you what I am saying. See, the rule of 8 is just slaughtered all over here. Alright, I'm going to stop it right here, and I'm going to show you some stuff that I've done. Alright, I've done several different demonstrations using this just simple magnetic film over the top of little magnets to show these wave functions. So what you're looking at there, hydrogen wave function. I'll just concentrate on what you see there. Now let's see what these specific arrangements of little magnets do. Now I'm going to put this right on top. Blip. Okay, now let me turn off the light so that I can get a better look at this. Okay, you should be able to see that all right. Now, what you see here is, well, you remember that. Okay, now, these magnets have polarities, even though they're round. These are the magnets right here. Right. Now you see that? That's 2 magnets together. That's 4. This is a single. Now you see the way the single shows it's intertwined? It's on its pole. I'm going to take another single. I'm just going to show you that is a single. They're very reactive. whoop, I'm sorry, that was a double, and the single was down here. But they are extremely reactive. Now, so if I, whoops, see, if all I got to do is get anywhere near this thing and they just go jiggling. Now, if I was to put this on there and roll it until it, see now it's right on its axis, I believe, so up and straight up and down. If I roll it over, you see you have a dark spot to the left and a white spot to the right. That's the negative and the positive. The dark is the negative, the positive, and it's just like the poles on the Earth, the North and the South Pole. Now, you can make very huge arrays of things with this and see all kinds of crazy interactions in here of these magnetic fields. You see that? You can just go on and on here and look at things forever. Now, I was trying to make different patterns that nature would make, and I don't know if it really means much, to be perfectly honest with you, but it's sure fun. Now, I'm seeing the same stuff. Whoops, let me paint this a little bit. I'm seeing the same stuff I see in the wave functions. You know what I'm saying? Now, how could we attach an atom to this? How would that attach? We know an atom can come along like this, or a molecule, and come up and hook into that. Now, what would that look like? Well, it looks like this. Now, how does that reaction here hook together? Almost like Velcro. I don't know if you can see that detail in there, but it's extremely intricate. Now, how does it affect the other regions way off to the sides and so forth? Let's try throwing a couple more little puppies in there. A little double here on the end. Let's see what happens. Because that's how molecules are made. They just glue together in little spots. Now, some of these places won't allow things to come in and attach to them. And other places say, yes, I want you here. Look at how much dark region that created and how much light region is there. That is an extremely attractive negative area right now, bordered by two extremely positive areas. I can't account for any of this. And then the second thing, I also cannot get these things to find their natural attachment points. What I do is I separate them out and I let them snap together naturally, so they hopefully will find their correct spot that they want to attach to. Otherwise, I could move this. I could take that magnet and I can roll it to a different spot, and it's going to have a completely different configuration underneath that foil. You really need a quantum computer to be able, because this is only 2D. You got 3D now when you go into the real world. So there's a whole bunch of, this is just gigantic, absolutely. Just nobody can figure this out ever. I don't think it's ever going to be able to be figured out. What you're looking for is stability here. And stability means that whatever particles came in here in their attached little configurations, like that one's got 4, this one's got 2, this one's got 12, when they hit together, they're going to glue into something called stability. Now, that's what you're looking for. They will try to find their most stable arrangement with their neighbors. It's just, they're very friendly. So if they find a stable arrangement, they will be, solid. They'll be strong. They won't come apart easily. But if somebody else comes along and has a more attractive partner for these particles, it will take one away. And then the other part of it will become disassociated and different. Now, will it be volatile? Will it be stronger? There's so many interactions. It's really, it can be figured out. I'm making it into a big deal. It's not, it's a big deal. It's pretty complicated. But it's not unsolvable. There's going to be regions that are more attractive than others. But I think you're going to need a supercomputer to be able to create that that big roundness of nature. All right, because that's what it is. It's just a ball of energy that's going on there, and they want to jiggle down until they feel comfortable, the most comfortable state. And sometimes they're not going to be comfortable no matter what happens. Those are things that are unstable. They fall apart. They are easily converted. They are reactive. Anyway, there's not much I can do, to be perfectly honest with, other than to say these are the different voltages, these are different spins, these are the different particles that they would decay to, and so forth. I can't really give you the numbers, like, oh, you're going to have, like this kind of stuff up here. I got to be honest with you, that's silly. In my mind, that is silliness. To come up here and just start going all these little jiggly numbers and this and that, and say that makes out, it's going to work out. Well, it never does. And then it's just all dark, spooky, and tangled, whatever. So I think better to go with solid evidence rather than, I mean, it's just too convoluted. That's just convoluted stuff. To me, very, very frustrating to try to talk to somebody about this when they start throwing these kind of things out, because they're meaningless. All right, so they can show all the models they want, and maybe they're right, maybe they're wrong. I don't know. I'm showing the things that I can stand behind and say, yes, here you can see what I see because I'm showing you what I'm showing. And when you see that light can be accelerated, light is a particle, light can be turned into plasma. We can tune, I believe, the frequencies of that light for a very, very short duration of time. But I do see different colors coming out when we start with red. It turns white. Well, let's look. All right, that's right, light from a red laser. And it literally is a particle that's coming through here in pulses, creating huge shock waves. These are all individual particles that light up because they are being concussed. That's what happens. What light does, it smashes into things, they glow. Now, this is stretched. I don't care how you look at this, that has accelerated. That is the particle beam in the center. Those are particles, you can see them, they concuss here and they become glowy white. And this is a Venturi here and here, 2 pins of steel. And by varying this and varying the size of the circle, we can, I believe, now I'm not 100% sure of this, but this needs to be checked. I believe we can tune the frequency coming out, but only for a very short time. And you say, why would I say that? Because I can tell you right now, that started red, it will come back to red. They do not change color. Once they come to the other side, they will be the same color they started out. How can it be white in the middle and come right back to that red? Now, it's either the same size particle, or somehow it got right back to where it was, because I'm going to show you. It came out the other end. You see that all spraying out there? You see that? That's the interference patterns they call it. Well, not interference. They're not like a wave splashing against another wave. Those are particles of negative particles. They're all trying to get away from each other, and that sets up these lines of interference between repulsion. That's what that is. It's not flappy little waves. And all of these little dots you can see here, I hope you can see them. Those little dots, those are the ether particles that float freely in the air. And these reverse concussive lines are the reverse EMF, reverse electromagnetic field. Enormous because of this concussion here. It's all related. So let's look at the other side of the Venturi. All right, they're coming out of the Venturi, absolutely glowy. Now they're yellow, and then they're going to return to red. Why? Why do they go back to red? And that's coming right out of the slit. The Venturi. And once they get into this range, they start to smash into the atmosphere, and they go and return to their red characteristics. But in the meantime, some of them are yellow, some of them are violet, some of them are pink looking. Now, why do they always return 100% back to red? However, we do see this. That little puppy there is a reverse spinning particle, it appears, because they all came from the other side of that Venturi together. They all started out as a red laser. They all exited out together, and that one is not displaying the same characteristics of the others. That one displays exactly what you would expect to see if it spun. Instead of a right-hand rule, it would left-hand spin, which instead of throwing electrons off around, it's pulling them back into itself. Now, that particle collided with one of these normal particles, or fields. Those are what's considered Higgs fields. Anybody say, oh, no, they're just this and that. Some people have very, very, very hard-headed people, just absolutely, oh, there's a flash, no, they're absolutely screamers, and they attack you every time you speak about this with absolutely nothing to say other than you're an idiot. You just got to read a physics book. Well, I read them all, and they are all wrong. They all started out, light cannot be accelerated. Everything's spinning away from everything else because light can't be accelerated, and we all started from a big bang, and that's why we know how far away things are. We have no clue how far away things are. None. None. They didn't all start from one place and go. Therefore, they are all somewhere, and wherever they are coming from, the light that's coming from there is slowing down coming from that. In two ways. Either it's so far away that it slows down, or it is being pulled back because of the attractiveness of the region it is coming from. So right now, as far as I'm concerned, we are lost in space.